My job tonight is to describe 13.7 billion years of cosmic history in about 45 minutes. To do this, I found it's expedient to leave out references to anybody else's work. And so basically, I'll make it sound like I did everything. What I want to talk about tonight is something really interesting, which is the history of the expansion of the universe. I'll tell you how we know that the universe is expanding, and I'll tell you how we've measured the history of that expansion. The big surprise is that the expansion of the universe is not slowing down due to gravity, as all of us expected, but is actually speeding up, and that there's a kind of runaway universe, which is the one in which we live. That means there has to be something else in addition to the usual kind of gravity, a sort of anti-gravity that we call the dark energy, and I'll try to explain what we know about that. So it's an interesting story, and it's a story in which Albert Einstein features prominently. This is a good thing, because if you associate yourself with Einstein, people have to take you seriously. Okay. So 100 years ago, exactly 100 years ago, when Einstein formulated his theory of general relativity, the theory of gravity that we apply to the universe as a whole, astronomers were very confident, as we are always confident, not always correct, but always confident, that the Milky Way, the system of stars of which the Sun is a member, was the whole universe. And so when people talked about the universe, they were talking about that system of stars. So I show you here a representation of the Milky Way. There's no place on Earth where you can stand and see the whole Milky Way. We see part of it in the northern hemisphere. You see it better if you're in the southern hemisphere, say in Chile, where the observatory that I had on the first slide is located. The most important thing in this slide, though, is not the Milky Way. It's this other galaxy over here. This is M31, the Andromeda galaxy. So I will repeat this method of misdirection, of showing you something and then saying that the important thing is the thing that you can barely see. In this case, the idea is, of course, that we live in a universe of galaxies in which it's not the stars of the Milky Way that are the constituents of the universe, although they are, but the individual galaxies, including the Andromeda galaxy, which is much more distant than the Milky Way, and that's why it appears small, that's why it appears dim, but it's equivalent to the system of about 100 billion stars in which we live. Okay, so here's Einstein at about the time of interest, and this is, of course, a photograph. It has some process, with chemistry and silver. You need to leave the shutter open for quite a long time, during which the person who was sitting here left, did not want to be seen next to Einstein, and this guy is shaking his head no. He obviously disagrees. One of the points I want to make is that the technology for sensing light has changed, that we have gone from photography like this to a silicon-based method of measuring the light using charge-coupled devices, CCDs. Now, the other thing that our technology has done is that it allows us to go back to old photographs and see what people were thinking. And it turns out what Einstein was thinking about the universe at this time is that it must be static, that is, neither expanding or contracting. And so Einstein, who formulated a model for what the universe might be like, added in by hand a little term that balanced out the attraction of gravity, that made a kind of static universe. And so here is where this is, in the back, can you see what this says in the back? Oh, too bad, because I was going to say it's in German and then, speak fluently. Anyway, this is from the paper where Einstein talks about it, where he justifies putting in this extra term, this cosmological term, which we use the Greek letter lambda. He says that term is necessary only for the purpose of making possible a quasi-static distribution of matter as required by the fact of the small velocities of the stars. So he wasn't wrong about the small velocities of the stars. What he was wrong was thinking that the stars were the thing whose motion would indicate what the whole universe was doing. That's just what's going on in the Milky Way. It was not for the next, until 10 years later, that astronomers changed their story from thinking that the Milky Way was the whole universe to knowing that it was just one among 100 billion galaxies that make up the universe. So that's the story I want to tell first. And here is Einstein talking to Willem de Sitter, a Dutch astronomer. And you know, they've got some lambdas in there. I'm not sure I'm not 100% sure it's the same lambda that we've been talking about. But anyway, that little thing is the term, this cosmological term, that Einstein put in by hand to make a static universe. But what astronomers noted was that we live in a universe that is, whose dimensions we can measure by understanding the properties of stars. And we have the idea now that you can get information about the universe in the past from the light that we receive. The speed of light is finite. In fact, it's small. You think it's high, but I think it's small. It's a foot. That's a unit of distance used in the United States and in Myanmar. A foot in a nanosecond. So that's a kind of a foot, sort of a normal size distance. So I see people down here, and I don't see you as you are. I see you as you were 15 nanoseconds ago. Curiously, the people in the back appear younger. And that's because I see them when the light was emitted, and it's 100 nanoseconds ago. Okay, just a silly joke in the room, but in the universe, it's not a joke. That is, when you receive light from distant objects, the light was emitted a long time ago. So a telescope is a no-nonsense time machine in which you receive light from the past, and that allows you to understand what was going on back then. And this story of trying to figure out the history of cosmic expansion is made possible by the fact that the speed of light is so slow, and when we go out at night, we see light that's been traveling to us for billions of years. Okay, astronomers in the same era began to understand the dimensions of the Milky Way galaxy, and interestingly enough, they found that we're not at the center of the Milky Way. So this is not really a picture of the Milky Way. This is a picture of a nearby galaxy that's something like our galaxy. And what we discovered in the early part of the 20th century was that the Earth and the Sun are not at the center of the Milky Way galaxy. So we're not at the, as you know, Earth is, probably you're familiar with this, even without taking Andy's course, that the Earth is not at the center of the solar system, when the Sun, it turns out, is not at the center of the Milky Way. In fact, Los Altos is located somewhere out here. And part of this progress of understanding where we are came from this demure woman, Henrietta Swan-Leavitt, who worked at the Harvard College Observatory, and she was a demon observer. And her observing was done on those photographic plates, the kinds of images that we had of Einstein, pictures of the stars. You could take pictures night after night. And while it was not considered proper for women to go to the telescope in those years, nevertheless, she was extremely effective in looking at these photographic plates and finding stars that got bright and dim and bright and dim. And she found that there was a certain class of stars that where she could measure how long it took to get bright and dim, and that was an indicator of how bright the star was, that is, intrinsically bright. You know, when you look out at night over, say, across the bay, you can tell a little bit which are things nearby and which are things far away from the brightness of the lights. And when you're looking far away, things look dim. When you're looking nearby, they look bright. The stars of the nighttime sky are kind of confusing because some of them are intrinsically very bright objects, but far away, and others are intrinsically dim objects, or relatively dim, but really nearby. And so sorting out which things are intrinsically bright, which things are dim, is a very important part of astronomy. In any case, Henrietta Leavitt found this certain kind of star, the Cepheid variable stars, where if you could measure the period, you knew how bright it was, and then from the apparent brightness, you could figure out whether it was nearby or far away. You could get a measure of the distance. At the same time that she was doing that, inventing this kind of technique, the technology made a big step forward, the technology of telescopes. So here I show you the 100-inch telescope. That's the diameter of the mirror, which is kind of inconspicuous in this picture down here. The mirror is 100 inches, about 8 feet across, and takes about 8 nanoseconds for light to get across the mirror. This, of course, is at Mount Wilson, up above Pasadena in the Los Angeles basin. At the time when the telescope was built, the population of Los Angeles, the village of Los Angeles, was 25,000. And it was a very dark and very good astronomical site. Of course, the growth of the big city has made the observations from Mount Wilson much more limited. That's not the place where we're doing the frontier work, although the telescope is still working in some ways. Now, again, this is a kind of misdirection picture because you might think the telescope was the most important thing in it. But really, the most important thing is the observer, and the observer sat in that little bentwood chair over there. Here's Edwin Hubble sitting in that chair. And it was Edwin Hubble, who was on the staff at the Carnegie Observatories at Mount Wilson Observatories in Pasadena, who used the telescope and photographic plates to find the same kinds of stars that Henrietta Leavitt had studied nearby in these fuzzy nebulae, these distant objects. And here's this picture of the Andromeda Galaxy, M31, from the 6th of October, 1923, so just 100 years ago or so. And you can see he's marked some things. He was looking for novae, new stars, so he marked those with N. And this one he thought was a new star. And then he looked back at the old plates, and he saw that he had seen it before. So it wasn't a new star, an exploding star. It was a variable star. And it turns out it's one of these stars like Henrietta Leavitt's, only it was 225 times dimmer than the comparable stars in our own Milky Way galaxy. That means it was 15 times as far away. So the distances that we're talking about are kind of interesting. If you go outside and look at stars, the light travels a foot in a nanosecond. It takes 10 years or 100 years or maybe even 1,000 years from stars that you can see when you go out at night. So you can look out and you can see stars where the light left, for example, when the Republicans were sort of sensible, and you can see even more distant ones when the Federalists, were in charge, and you can see light from stars from hundreds of years ago. When you look at galaxies like M31, you're seeing something that's much farther away. The light has been traveling to you for a much longer time, and the nearby galaxies have light travel times of 1 million years or so. So they're 1 million light years away. Okay, so that's one part, distance. The other part is velocity, and how do we measure the motion of the galaxies toward or away from us? Well, I wrote this haiku, stars are made of atoms, the same as atoms on Earth, and the galaxies are made of stars. Well, I put in some prepositions so you could understand it. Anyway, so here's a picture of the sun. The sun is made up mostly of hydrogen, but the hydrogen atoms in the sun behave exactly like the hydrogen atoms in the laboratory on the Earth. The calcium atoms on the sun, the same as the calcium atoms that you might have in a gas tube on the Earth. And the reason that's important is, first of all, we can tell what things are made of, but so when we take the light from a distant object, we can find out that the elements that are common on Earth and common in the sun are also common in other stars and other galaxies. So here's the idea. You take the light from a star and you spread it out into a spectrum or rainbow. And you know what the astronomer's job is? The astronomer's job is to take something beautiful and to turn it into a graph. And that's shown up above, which shows how much light there is at each wavelength or color. And you can see that there are those sharp places where there are sharp dips. It's even more conspicuous when you look down here. There are lines that go across the spectrum that are places where the atoms in the atmospheres of the stars are absorbing some of the light. And those are set by the physics of the very small world, the world of quantum mechanics. Those are set by the properties of hydrogen atoms or calcium atoms. And those, we think, those properties are the same on the Earth the same on the sun, the same on distant galaxies. However, when you take the spectrum for distant galaxies and you measure it, and here's somebody in the process of doing it in that era, again with photographic plates at the Lowell Observatory, what astronomers found was that almost all the galaxies are moving away from us. The objects that are coming toward you, turns out, the spectrum is shifted, compressed a little bit and shifted to the blue, and the ones that are going away are shifted to the red. If, for example, you go down to the Pacific Coast Highway, if the speed of light were 1,000,000 times slower, then the cars that were coming toward you would have blue headlights, and the cars going away from you would have, well, they do have red, but anyway, it's for a different reason. It's for a different reason. So you can tell which is coming toward you, which is going away, and it turns out that when you measure the galaxies, except for a few of the very nearest ones, the motions are all away from us. All away from us. I let that sit there for a while. Okay, now, so Hubble had measured distances in the way I described by finding certain stars and judging the distances from their brightnesses. And Slipher had velocities, the fellow I showed you before, had velocities for some dozens of galaxies in the mid-1920s. So why didn't they put 2 and 2 together? Well, I read Hubble's book on this subject, The Realm of the Nebulae, which he wrote in 1936 after kind of doing all this work. And he said, he has a kind of physics of psychology. He says, natural inertia. A natural inertia in the face of revolutionary ideas, couched in the unfamiliar language of general relativity, discouraged immediate investigation. The passive voice was used. I think he means, I didn't understand general relativity, and so this was a puzzling thing. And he was, although there were people, Eddington in England, for example, who were telling astronomers that they should pay attention to general relativity, and even had a table of Slipher's velocities in his book on the nature of relativity, the message did not quite get through to the astronomers. And it's not so surprising. They really were not. The distance between physics and astronomy at that time was bigger. However, by 1929, Hubble did do this thing of measuring. He had measured some distances, highly inaccurately it turns out, but anyway, had measured distances and plotted Slipher's velocities this way. So this is what we would call today, we would call a Hubble diagram. Hubble called it figure 1. And it shows velocity going this way, distance going out that way. And here's 0. You can see that there are a few galaxies that have velocities below 0. That means coming toward us. But almost all of the ones in his sample were going away. And there's an interesting relation between the two. You know what a scientist will do if you have 2 lists of numbers, the distances and the velocities. You'll plot them up against one another and look for a relation. And here's the relation, that as you look at larger distances, the galaxies are moving away from you faster. So nearby galaxies are moving away, but if you go twice as far, the galaxies are moving away twice as fast. Now, not so long ago, I said, you know, we know the Earth is not at the center of the solar system, and everybody chuckled because we all know that. And I showed you that the sun is not at the center of the Milky Way, and that seemed funny too. But this this is something different. This is the whole universe moving away from us. And I want to try to convince you that the egocentric view of the universe, shown here, is not the correct one, a correct interpretation of Hubble's diagram. So the idea, of course, this is quite popular among the undergraduates at Harvard, that they might be at the center of things, and certainly among the tenured faculty, this is the prevailing view. So how can it be that the velocities are bigger as you go away in all directions, but we're not at the center? And I will hope to demonstrate that through the use of a cheesy animation. So here we go. Here's the cheesy animation. All I've done here is take a picture of some galaxies and make it bigger, and then show it to you in stages. And what you can see, I picked this galaxy, but I could have picked any other one. If you look at the galaxies that are nearby, these little flecks here show you that in the time of this expansion, it moves a short distance. But the ones that were farther away, say this one, which was several times as far away at the beginning, also moves farther away. It's just expansion in all directions. So another way to say it is, if the universe is just stretching out in all directions, expanding, then to any observer, it's going to look like everybody's moving away from you. If I had the power vested in me by the buildings and grounds people here at Foothill College to make this auditorium twice as big in all dimensions, think about what it would look like. Your neighbors would be moving away from you, no offense. But the people on the other side of the room would be moving away from you faster because they would double their distance in the same length of time. So it's like stretching out in all directions. So that, if you believe that, I have achieved my goal. Uh-oh. What is this? Perhaps I have not achieved my goal. Oh, yes. Sorry. This is a fancy dissolve. Excuse me. So here's a picture. So what could cause that? Well, remember that cosmological constant that I talked about at the beginning? Here's a picture from a Dutch newspaper in the 1930 that shows lambda, that is the cosmological constant, making things blow up. Now, English is a dialect of Frisian, so you can read Dutch. It says, what makes the ball get up? What makes the universe, the everything, swell up? That has to be lambda. No other answer can be given. Of course, I have the translation over here, so it makes it easier. So what about Einstein? Einstein, you remember, had put this in to make a static universe, but by 1930 it was pretty clear that wasn't true. And maybe that lambda had this role, but Einstein didn't really like it very much. So here's a picture. Here's Einstein. There's Hubble. This is the observatory director, hoping that Einstein will not break the 100-inch telescope. And here they are in the library at on Santa Barbara Street in Pasadena. The library looks exactly the same, only the people have changed a little bit. Anyway, and here's Einstein, of course. Here's Hubble. And the man patting Hubble on the head is George Ellery Hale, the man who built the world's largest telescope 4 times, including the 60-inch and the 100-inch at Mount Wilson and the 200-inch telescope at Palomar. Well, what did Einstein think about this expansion after he'd gone to all that trouble to have a cosmological constant? You know, Einstein is such a powerful figure that people have collected his postcards. And here's one he wrote to Weil, a well-known physicist, a mathematical physicist. And here it says, if there's if there's no quasi-static world, then the heck with the cosmological constant. I translate freely. You know, he was pretty quick to give it up. And if you go to the National Academy of Sciences in Washington, there's a wonderful statue of Einstein. Here it is. And on it, he has this tablet, which apparently he brought down from some mountain. And if you read it, if you climb up on the statue, the park police are coming. There's this equation, E equals mc squared. That's probably the only equation that most people know from physics. This is the equation that describes the photoelectric effect, what happens when a photon lands on a metal and kicks out an electron. Give him the Nobel Prize for that, because this one is too complicated. Up here is the basic equation for general relativity that tells how the presence of matter curves space. The interesting thing about this formulation is there's no lambda term in there. Einstein not only stopped using it, he didn't just set it to 0. He just took it out of the equations and didn't talk about it anymore. And the conventional thing, and the thing I alluded to in the title when I talked about this being Einstein's blunder undone, is that we often call this Einstein's greatest blunder. And I wondered myself, why do we call it that? You know, who said it was his greatest blunder? Because you cannot find any written thing where Einstein said, this is my greatest blunder. You can find a postcard to Weil that says, well, maybe we don't need it, but that's not the same thing. And I believe the culprit is George Gamow. When I was a kid, reading science books. Some of the books I read were by George Gamow. a great writer, and the author of his autobiography, of course, called My World Line. And here he talks about this. He said, Einstein's original gravity equation was correct, and changing it, that is, putting in the cosmological constant, was a mistake. Much later, when I was discussing cosmological problems with Einstein, it's a phrase I wanted to have in my book, too late. Much later, when I was discussing cosmological problems with Einstein, he remarked that the introduction of the cosmological term was the biggest blunder he ever made in his life. But this blunder, rejected by Einstein, is still sometimes used by cosmologists even today. And the cosmological constant denoted by the Greek letter lambda rears its ugly head again and again and again. Okay, George. Anyway, George Gamow didn't think the cosmological constant was such a good idea. But what I'm going to show you tonight, if I get to it, is that by looking at supernova explosions halfway across the universe, we've been able to trace out the history of cosmic expansion, and it shows this very strange property, that the expansion's speeding up. So I better speed up. When I read this book, though, The Realm of the Nebulae, Hubble's book, I had to read it again recently because Yale University Press put out a new edition and they wanted a new foreword. And I thought, well, they don't really need a new foreword, but if you're asking me, okay. And so I had to read the book again. And Andy Frackner and I read this book in 1967. Well, we were assigned this book in 1967. And I had the same experience that I had with Great Expectations, which was when I read it in high school, Pip, the protagonist, seemed like he was sort of a high school kid. And when I read it again in college, he seemed to be older. And in the same way, when I read The Realm of the Nebulae the first time, I thought it was about nebulae, about the galaxies. The next time I read it, 2 years ago, I thought it was about supernovae. Here's what he said. Supernovae, these are exploding stars. Here's a star in a galaxy. They're at the same distance. This one star, for a little while, is as bright as about 4 billion stars like the sun. Supernovae can be detected at immense distances. And in principle, they are a criterion of distance about as reliable as that of total luminosities of the nebulae. That's what he was using for the more distant galaxies. Actually, however, Hubble grew up in Missouri. But he was one of the very first Rhodes Scholars, and so he went to Oxford from the University of Chicago, and he came back with an English accent, and he came back saying things like, actually, however. Actually, however, the maxima are so seldom observed, and the supernovae themselves are so rare that they contribute very little to the present problem. That was right. And what I want to show you is that the advance of technology, the same things I've been talking about, the change from photography to silicon detectors, has changed this whole story, and the supernovae now contribute a great deal to solving the problem. The first step along that path was to find these supernovae and to study them, and the person who did that was Fritz Zwicky. And here's Fritz Zwicky at Palomar. This is the first telescope at Palomar. It's the 18-inch Schmidt telescope at Palomar, which had a very wide field. It was a very novel optical design, and he used it to search for supernova explosions. It turns out they are very rare. They're about 1 in 100 years in a big galaxy. So if you have a graduate student and you want them to do a thesis, they can either stay for 100 years or learn to study a lot of galaxies. So here's an image to show you what these things are like. This is a one star, which for about a month glows as brightly as 100 billion. And if you use the brightness of those stars as your gauge of distance, you can make a plot like the one Hubble did. So here's a plot, and it's the same kind of plot I showed you before, velocity going up this way and distance out that way. And you can see that the relation between velocity and distance that Hubble found from the galaxies he had nearby holds over this bigger distance. This is a velocity that is about 1/10 of the speed of light, and this is a distance. These are astronomers' mysterious units to keep the physicists at bay. This is a distance of about 2 billion light years. This is sort of the neighborhood. And there is expansion, all right, of the kind that Hubble saw. Hubble's Hubble diagram, the one that I showed you as figure 1, would fit in this little red square down here at the beginning. So the span of distance over which we've measured this effect is much bigger, but we see the same effect that he did. And what I'll show you is we can go much farther into the past by using the most advanced technology and really see about this history of expansion. Let me just say a couple words about the supernovae. Here is a rather fanciful woodcut of Tycho in 1572, going outside and looking up in the constellation Cassiopeia, which you might recognize up there, and seeing a new star, which it turned out was not an ordinary changing star, a variable star. It was a supernova, an exploding star. If we go there today to the location that Tycho measured, this is what we see. Well, actually not what we see. This is what's there, and we represent it. This is the fluffy stuff that's green is X-ray emission from the very hot gas that's inside the explosion. The blue stuff is radio emission that takes place as the supernova explosion propagates out into the gas between the stars. And the optical emission is quite inconspicuous in this picture, although I have studied it. But what you can see is that this is the shreds of an exploded star. We think we understand how they happen, that at the end of their lives, certain kinds of stars, the sun won't do this, relax. The certain kinds of stars can explode as in a thermonuclear explosion, where the hydrogen and helium, well, really the carbon and oxygen in the core of the star, burns suddenly, like a bomb, to make iron, the most tightly bound nucleus. And of course, you should be interested in this, because if you have iron in your blood, where did it come from? It came from supernova explosions and stars that lived and died before the Earth formed 5 billion years ago. The universe is about 14 billion years old. The sun in the solar system is only about 5 billion years old. So there was a long history before the sun and before the Earth when stars were exploding and making these elements. So if you have a 1951 Pontiac, as I do, and you ask, where was this made? The correct answer is not Detroit. The correct answer is that it was manufactured in supernovae over 5 billion years ago. Okay, so here's a little animation that we made of a supernova. I'll go back. Sorry about repeating a not very good joke. Okay, and this is sped up. It's about 2 months worth of observations, and you can see that the supernova gets bright and dim. The problem is that they are rare. I said that Tycho saw one. That was in our own Milky Way galaxy. Kepler saw one in 1604. That's the last one for which we have data. I mean, visual observations, for which anyone saw the explosion. And so it's been, 400 years. So it's kind of time for another one. If we only had an astronomer on Earth sufficiently wonderful to be compared with Tycho and Kepler, we would have a supernova, but no such luck. And I know my colleagues. Okay, so let's trace the technology here a little bit. Here's my thesis advisor, Bev Oak, in the 1990s, and he's holding a charge-coupled device. This was a fantastically expensive piece of equipment that had been fabricated, probably not far from here, and it was a 0.24 megapixel camera, and you can see it made him happy. Now, what Moore's law shows is that the astronomers are still happy, only the things that make them happy are much bigger detectors now. So this is John Tonry, and this is one of the detectors that we've been using in the work that I'll allude to in a minute to spine supernovae, and I'll show you how we do it. So here's the idea. The idea is you take a picture and you compare it to a picture from, let's say, a month ago. I said the supernova takes about a month to get bright and get dim, so that's kind of a good time period. And if I said there's one supernova every 100 years, well, if there were 50 weeks in a year, like if you were in France and you took extra weeks off or something, anyway, then that would be 5,000 weeks. So if you look at 5,000 galaxies, you have a pretty good chance of finding a supernova that's less than a week old. And if you look at 10,000, which it turns out in this picture, there are several thousand galaxies, you have a pretty good chance of detecting a supernova. Not in these galaxies, of which there are only dozens or hundreds, but the ones that look like little tiny flecks, those little ones at the edge of what you can see, those are the ones where you should be able to find a supernova any night. So the technology was just getting good enough to do this, and I had a very good graduate student, Brian Schmidt, And here he is explaining to his thesis advisor how easy it's going to be to write the software to do that. And I said, well, you know, there's this other group at Lawrence Berkeley Lab, and they've had 5 people working on it for 5 years. He said, yeah, it'll take me a month. And so it did take him a month. It was really bad software, I gotta say. But it crashed a lot, but it did also help us find supernovae. So here's the idea. Here's a picture. Suppose this is about 1/1000th of the image area of the detector I showed you a minute ago. So here's a picture, say that was tonight. And this is maybe a month ago. And the idea is not so complicated. Subtract, these are digital images, so you can subtract them. Subtract this image from that image, and what's left over will be the things that have changed. So if there's a new star, and there is, in that little fuzzy thing, there is a new star. It's kind of hard to see just with your eye, but when you do the subtraction, there's no question about it. Plus, it has a red circle around it, and I used that several times tonight to show you what's the important thing in the picture. So that was very good. Brian wrote the software, and it worked. The other thing, and I wasn't completely frank with you when I said you can judge the distance to stars from their apparent brightness, because of course there are other things that can make stars dim in addition to the distance. For example, dirt. So here is interstellar dust, as we call it. So here's a picture of another galaxy that just shows you that in the neighborhood of the exploding star, there might be additional dirt. And you can see how this would be a problem. If you measure something of a certain brightness, you would infer a certain distance, but if it has been dimmed, not by distance, but by dust, it's really closer than that, and you've made an error in the distance. So if you're trying to trace out the relation between velocity and distance, you'll make a mistake. And so I thought about this, and I thought, you know, there must be some way to do this. The dust absorbs blue light more than red light, so maybe by measuring the colors, you could figure this out. And I had a very good student. Here's Adam Rees. This is the day, it's not a very good picture, but anyway, the day he passed his PhD exam, and here's me wearing all the answers. And he worked out how to do that. So as I mentioned, there are 2 groups working in the field. There was Saul Perlmutter's group working at LBL, and our group, a little more motley crew. But we had good exchanges with Saul's group, and we outweighed him by quite a bit, so that was good. In 1997 and into 1998, we began to get some results that were really interesting. Adam had gone to the Massachusetts Institute of Technology as an undergraduate, where you learn to keep a lab notebook, not to patent things, just to keep track of what you're doing. And so here's his lab notebook, Hubble results, blah, blah, blah. And he says, well, if the lambda is 0, that's what he means here, then for a Hubble constant of this value and so on, you get a value for the fraction of the universe that is gravitating stuff of minus 0.36. So at that time, I was on sabbatical in California, and he called me up. He was in California, too. And he called me up, and he said, you know, I got negative mass. I said, well, that's got to be wrong. You know, that's got to be wrong. And he said, well, I think I've done it right. And so he said, there's something missing. And I said, well, you know, it could be the cosmological constant, but Einstein said that was a very bad thing to even talk about. So I don't really want to talk about it. Nevertheless, the kids convinced me that you had to look at the data. So here's a diagram, something like the one I showed you before, but this range of, this is velocity and distance, sorry, it's switched around. Nevertheless, the velocities and the distances here are much larger. The one I showed you with the supernovae went out to about 1/10 of the history of the universe and 1/10 of the speed of light. This is going out about halfway. And these are the distant ones that were found by techniques like the ones that I described. Our team did all the blue ones up here, few but small scatter. And we did all the ones down here, both the blue and the red. Saul's group did the red ones, and there are more of them with a little more scatter. When you take out the 45-degree line and you ask yourself, what was the universe doing back then, you find out something interesting. Here's the idea. If the universe is going at a constant rate, then the velocity will be proportional to the distance, all right. If the universe has been slowing down due to the action of gravity, then the distance that the light will travel in the time it gets to you is a little less than it would be in a universe that was expanding at a constant rate, and the supernova will look a little brighter. If, on the other hand, the universe is accelerating, which we didn't think was possible, nevertheless, then the supernova would appear a little dimmer. And in this plot, you can see that if you look nearby, that's just noise. But if you look far away, it's a little noisy, all right, but the points lie up, which means because we're astronomers, up means dimmer, means the supernovae are a little dimmer, as if the universe is stretched out a little extra bit while the light was in flight. Here's the way we usually plot that up. We say, well, there's something that's slowing stuff down, there's something that's speeding things up, called one of them the dark energy, the other the dark matter. And the measurements that I just showed you from 1998 for our group and 1999 for Saul's group are shown here. And you can see that they agree pretty well, but they're really pretty rotten because there's a lot of room. Nevertheless, if you, in 1998, 6, if you walked up to a theoretical astronomer and you punched them in the arm, which is always a good, nice way to say hello, and you asked them, where do you think the universe will lie on this diagram? They'd say, we know where it's going to lie. It's going to lie right there. It'll be a universe that has just enough dark matter in it so that the universe will expand but forever, but always slowing down, and that the geometry of the universe will be right on the boundary between a space that is closed and one that's open in Einstein's universe. So here's what people thought. If you we had a tough time because I thought that the correct answer was here at about 0.3 and 0. And so the theorists, who are very confident people, would kind of lean over you at a meeting and say, well, they'd say, that's a very difficult measurement, isn't it? And you'd say, yes, that's a very difficult measurement. They said, well, you just keep at it, they said. You're gonna find this. Well, so, whoops, what did I do? Oh, here we go. So, finding a value in here, these contours, these zeppelins, mean that you have a 2 out of 3 chance being inside this one, a 20 to 1 chance of being inside this one, and a 1 in 200 chance of being inside that one, all but 1 in 200, seem to indicate that you didn't have 0. You had some real value. Okay, so this was a big surprise. Even Einstein was surprised, now he's carrying around this sheaf of papers. So those of you in the front row can see it says lambda on it. So that's from 1998. So the idea is that there's a kind of tug-of-war between these two things, gravity trying to slow things down, and this other stuff, which has a springy quality, a kind of anti-gravity quality, trying to speed things up. Well, what have we done since 1998, aside from going around picking up prizes? The answer is, we have filled in this diagram. So this is over the same range as the one I showed you before. There's some space telescope observations up here. There are ones from the camera that I showed you with the guy with the blue shirt, and there's a whole bunch of nearby supernovae. And you can't see it because the plot is drawn in such a kind of stretched way, but this line is curved. And it is curved in the way that corresponds to an accelerating universe. So if you put it on this diagram, what's allowed is now down in here. And you can see that 0 is not a good answer for the amount of dark energy. And that when you put this together with other information from the cosmic microwave background and from how the galaxies are clustered, we really are closing in on a universe that has this weird property, that it requires something that has this kind of expansive, repulsive part to it. Now, the data is so good you can do the analysis yourself, okay? So here I've plotted up the distances and the velocities. And what's happening here is there are plots here with different lines that correspond to different values for this thing that we call omega lambda, the fraction of the energy density of the universe that's in the form of the dark energy. And you can see that 1 is too much and 0 is too little. And that looks pretty good. That number was about 0.7, which means that 2/3 or maybe 3/4 of the universe is in this weird form. So in 1998 and beyond, what we found is not just that the universe has a little of this, but that it's mostly this stuff, this weird dark energy. So now you can do it. But, you know, what the real prize is to do it the first time. Or as Galileo said, all truths are easy to understand once they are discovered. The point is to discover them. Okay, so just to indulge me for a second, here I am in the Grand Hotel in Stockholm as Adam and Brian are getting ready to receive the 2011 Nobel Prize. In the old days, the professor would have gotten full credit for everything. Anyway, so here's our picture of the universe. This is a very strange picture in which atoms, the stuff I was talking about before, having all those lines and calcium and the iron and all that stuff that we're used to, the things that make up stars, the glowing stars, and all of that is only about 4% of the energy content of the universe, the stuff in the universe. The other chunk of gravitating stuff is in some other form whose nature we don't really know. We look to our physics friends to help us identify what this might be. We call it the cold dark matter. It might be weakly interacting particles. They might be something that you could find on the surface of the Earth, or where you would get, or coming through the Earth, or that you might get clues to their nature in particle accelerators. We don't know what it is, but it makes up about a quarter of the universe, and 3/4 is this crazy stuff, the dark energy. Now, I don't know how you feel about this. I feel pretty good because, well, the diagram is full. And of course, you should ask, what is it full of? And in this case, I think it's full of our most important resource for scientific research. It is full of ignorance. We don't know what that is, so that means we have a chance to find out. We could do it. We don't know what this is. It could be the cosmological constant, as I'll say in a minute, but it might be something else, and we'll get a chance to find out. So the thin little slice there that we're in is another way in which we're not at the center of things. The atoms in our bodies, the atoms in the Earth, the atoms in the stars, the atoms in all the galaxies and the gas between the galaxies, it's not much of everything. It's not everything. In fact, it's a very small fraction of what's out there. But I got to say, it's the most interesting part. I mean, you know, you can make a pumpkin pie out of baryons, these heavy particles. So what is the dark energy? Well, in the old days, when Google was young, you could Google dark energy, and instead of getting a kind of self-congratulatory website from a large government organization, you would find this from American Hydroponics. Dark energy is a kind of fertilizer for growing controlled substances in your closet. And the advertising copy said, these specialized processes are also responsible for the very distinct odor of dark energy. So we don't really know what the dark energy is, but we know it smells bad. What about the dark matter? It seems like a very strange story that we look out into the universe and we see galaxies. But what I said was the galaxies are not the gravitating stuff themselves, and the motions of stars in galaxies also show us that. The motions, the light is just showing us where the mass is. In the same way that what you're seeing here is the snow, but the snow is not the mountain grasshopper. And then the travelers down here crossing this path. Okay. So what about this dark energy? Why do we think this is real? We think it's real because we see its effect. You know, if you look outside and you see the trees moving around, and somebody says, well, that's the wind. They don't see the wind. They see the effect of the wind. And at first that sounds like somebody being fussy. But really, in the same way, we don't see the dark energy exactly. We see the effect of it on the history of cosmic expansion. Okay, I better hurry up and say a word about the future. First of all, we want to find out if the dark energy is the cosmological constant, which now the same people who told me the universe was made entirely of dark matter are telling me they know that it is the cosmological constant. Okay, could be true, but maybe we ought to measure it, is all I'm saying. If you ask theoretical physicists, could they please estimate the energy associated with the gravity in the vacuum, they say, certainly. They shoot back their cuffs, they take out their Mont Blanc pen, and they write on the back of an envelope shown here something that has the fourth power of the Planck mass, and it is a number of about 10 to the 120th, where the correct value is 0.7. This is what, in polite academic circles, we call not good quantitative agreement. What other people would call wrong. So there's a real puzzle. Why is the energy associated with the vacuum so small? And it is a real puzzle to which people do not know the real answer. Another way to ask it that is not quite so radical is to say, well, all right, I don't know why it's so small, but is it the cosmological constant? Does it behave like the cosmological constant, which lives up to its name, it's constant? Or is it something else, something that changes over time or changes as the universe expands? So I feel entitled to investigate this because I have received a union card from the International Brotherhood of Theorists. It's valid to infinity, and it's signed by a guy who won the Nobel Prize. So that's good. But this really is a puzzle, and making the measurements, I think, will be a valuable thing to find out what the nature of the dark energy is. But it's a universe that in some deep way is kind of unsatisfying. It doesn't really make sense. And so I've had to tell my students that, well, the universe doesn't care whether it makes sense to you or not. And I said that in a pithier way, and somebody put it on a T-shirt. And I was at an academic institution, and they had them for sale. And I said, hey, I'm Robert B. Kirshner. They said, we'll give you a good discount. Okay, so what is the solution? Well, one way to think about it might be that you could put something like the cosmological constant on the right-hand side of Einstein's equations that I showed you earlier. I'm wearing the same jacket. Hey. What a coincidence. And, you know, that it would act like something to propel the universe. Then the park police came. Okay. What are we going to do? Well, now I have time on the Hubble Space Telescope. We've been using the telescope that uses that big detector I showed you to find supernovae. So here's a supernova next to a galaxy. Then we tell the position of that to the Hubble Space Telescope, and sometime later, like next week, they point it, and here's that galaxy, and here's the supernova. These measurements are made at longer wavelengths than you can do from the ground. In the infrared, it turns out the supernovae behave even better, and the dust is less of a problem. So we think this is really a great way to get more accurate measurements that will tell us whether it's the cosmological constant or not. Keep your eye on this space. There is the James Webb Space Telescope, which is supposed to get launched in 2018. And it will work in the infrared. It will be a tremendous, it's 6.5 meter diameter once it unfolds. And, it will be a wonderful tool for this sort of thing. On the ground, people are working on building big telescopes too. Here's an image of the 30-meter telescope that the Gordon Moore Foundation has been helping the University of California and Caltech and an international consortium of astronomical, Japan, India, Canada, and China are working together to make this telescope. What is this? Oh, they're very big about the logo. Okay, just to give you an idea of what that telescope might do for this kind of problem, let me just show you. Here's a galaxy. This is with the Space Telescope. Here's a galaxy, and here it is with its supernova. Here's another galaxy, kind of a spiral, and here it is with its supernova, as measured with the Hubble Space Telescope. The big telescopes, if we correct properly for the blurring from the Earth's atmosphere with the technique we call adaptive optics, we are going to get images that are 10 times sharper than with the Hubble Space Telescope. So here's, I've drawn it here. Here's sort of, if you were at a good telescope on the Earth, this dot would be blurred out to about that size. If you work out what the blurring ought to be for the Hubble Space Telescope out in the infrared, it's about this size, and sure enough, it's about that size. What I'm saying is, when we have these big telescopes, and it's not going to be for another 10 years or so, and we get the adaptive optics working, we're going to have imaging that will allow us to to see a point source next to a fuzzy thing and measure the properties of the supernova, if that's still of interest, with fantastic precision. We collect a lot of light and we make it much sharper. Okay, well that's enough. I can't recommend a better book than this one if you want to learn about exploding stars, dark energy, and the accelerating universe. And finally, I want to close by saying a word about what kind of science this is. When I was president of the American Astronomical Society, I would stand next to presidents of other societies, and we would speak to authorities, and we would say things like, well, science is very important for technology, and science is very important for defense. And a lot of the congressmen are kind of old guys, so you'd say, and for medicine, that would be good too. And these things are all true. Everybody wants to be rich. Everybody wants to be safe. Well, immortal may be a little strong. But anyway, people like to be healthy. But this is not the kind of science that you do for those reasons. I think this is not a vision of an ideal world if you were rich and safe and immortal and bored. That we are curious. We want to know, where did we come from? Where are we going? What time is it? And these cosmological measurements are part of the story of what people want. So I think a good reason for doing this sort of work, it's not for all science, but for this kind of science, is for the joy of finding out how the world works. Thank you very much.